So fantastic. Thank you so much for inviting me to speak, both to Abraham and to Frank and to all the other organisers. It's a real pleasure to be talking to you today. I'm a mathematician. I'm a mathematical biologist at the University of Bath. So I'm going to be talking a little bit about some of the mathematical modelling that we've done in trying to understand how randomness can impact on locust swarms. We try and keep the maths to a relative minimum if I can, but there's a couple of slides where you can just glaze over if you want and forget about the maths. So the research I'm going to tell you about actually comes from an experiment that was done back in 2006 by a group at the University of Oxford, including the lead experimenter, Jerome Bull, who was certainly registered on this conference, although I'm aware that it's very late at night for him in Australia, so he's probably gone to bed by now. But yeah, so they did an experiment back in 2006 to try to understand, for some reason the slides have just disappeared from me. Oh, here they are. Okay, grand. So they did this experiment, and yes, if you can press play, they looked, videoed from above, locusts in this ring-shaped arena, and when you put a few locusts into the arena, nothing much interesting happens. But then when you start to put 100 locusts into this arena, then you can start to see what they do. They march around in the same direction around the arena collectively, almost all of them, except as you can probably see, there's one guy that's going around the outside at the right hand side at the moment. He won't be told which way to go, but most of them tend to go around the arena in the same direction for the whole duration of the experiment. When you put some intermediary number of locusts into this arena, somewhere between so maybe around 30, 40 locusts, they do the same marching together around the arena, but then they actually switch directions spontaneously and they start marching in the opposite direction around the arena. So if they were going clockwise, then they go anti-clockwise, or vice versa. All right, so you've seen the video now, and maybe we can go back to the slides quickly. So they did these experiments where they put these locusts into this ring-shaped arena. There was a big boundary around the outside. It's about 90 centimeters wide, and then there's this block in the middle where the locusts weren't allowed to go to make it into a ring-shaped arena. And so they found this collective behaviour of the locusts, and I'll just show you. This is the experimental setup that they had. So camera mounted on the roof, looking down at this ring-shaped arena with different numbers of locusts in it, and then they recorded these videos of the locusts. So we can skip past the movie. So what did they find in these experiments? They found that these locusts exhibit collective motion. So this is an emergent property of the behavior of these locusts. They tend to move together without any coordinated control. No one is telling them what to do. What we also found was that these locusts were switching between these two steady states, one where the locusts move around clockwise and one where the locusts move around anti-clockwise. And they also found that this was a noisy or stochastic process. So randomness was important in this process, and it allowed these locusts to switch from one direction to the other. And what they found was that the more locusts you have in this arena, the longer the locust will stay going around in one direction. And they thought of that as a proxy for the stability of the swarm. So how stable or unstable is the swarm depends on how often they switch back and forth. So that's what they found. And then this is a typical experimental time course. I've lost slides again. Oh no, not yet. Not this one yet. Sorry, Abraham. I'll give you a shout. Not this one yet either. I just wanted to show a couple back on the slides. I'll give you a shout when it's time to play the next movie.
Sorry.
No, it's fine, don't worry. So they had these experimental time courses with the locusts. So what they did is to assign every locust that was going clockwise a value of 1, and every locust going anti-clockwise a value of -1, and effectively just added up all the +1s and -1s to get a sense of the alignment of this swarm. So here you can see a typical time course where if the value is roughly at -1, then all the locusts were moving anti-clockwise, and if it's a +1, then roughly most of the locusts were moving clockwise. And you can see that they stay in one direction for a while, and then they switch to going in the other direction, and they switch, and they switch and switch. And when you put in more locusts into the arena, say 60 locusts, then the locusts will stay aligned for the duration of this experiment. So maybe we could have that first movie of the landscape. Great. So we thought, what can we do to model this mathematically? And the idea is that you can think of this as a stochastic differential equation. Okay, so I know a lot of people won't know what it is. The idea is that you think of looking down on top of a valley, which is what you see in this movie. There's two valleys separated by a hill. And what I want you to think of is a beach ball being blown around in this valley. It's moving according to some random noise units. And so what you see is when you put this beach ball in this valley, you can watch how it moves around. So perhaps you can move to the next movie, Abraham. Perhaps you can move to the next movie. Thanks. So this is the beach ball, this red dot, and you can see this is the beach ball, this red dot, and you can see going into this right-hand valley, and then eventually it will switch back to the left-hand valley, and it will move around stochastically. And you can start to see that the trajectory that this beach ball is mapping out is quite similar. Is quite similar to the storms we're making in the experiment.
Yes, sorry, look, make your...
Sorry. Oh, it stays in one direction for a while, and then it goes to the other direction for a while. So we thought, well, this is the sort of behavior we want to replicate. But ideally, what we'd be able to do is to do this using a mathematical model which actually accounts for what the individual locusts are doing. So perhaps we can go back to the slides, and I can explain to you about a particular type of model which is called the self-propelled particle model. So these self-propelled particle models, we take each locust. Abraham, could we get back to the slides, do you think? Thank you. We take each locust and we model it as an individual which has a position and it has a velocity and it can interact with its neighbors. So this is what the original experiment looked like. It was these locusts moving around with these positions and velocities in the ring. We tried to simplify that, and so I model each of these locusts as a point particle. So that's what these black and yellow circles are. They have a direction of velocity, which is these red arrows, and they have a position around this ring. And then they also have the ability to interact with their neighbors. So this green part of the circle shows for this focal locust how it interacts, which neighbors it can interact with. So the other thing that we do to make this a little bit more simple is to take this domain and unwrap it so that it sits just on a one-dimensional line, and then anything that goes off at the right-hand side of the domain comes back on at the left-hand side, and similarly anything that comes off at the left-hand side will go on back on at the right-hand side. Okay, so that's the idea of the model. This is the most mathematical slide, so don't worry too much about this. But all this says is that each locust, which is indexed with the letter I, will change its position by updating using its velocity, which is called UI, and multiplying it by the time step. So we take this moving forward in discrete time steps. And then this is how the locusts update their velocity in each time step. So they look around themselves within this radius R, this distance that they can see each other, and they measure the velocities of their neighbors. And they take an average of that. So they sum over all these velocities and they add them together and they divide by the number of locusts they can see. And that's their average velocity that they can see, this UI lock bar. They plug that into some moderating formula. They can take an average of what their neighbors are doing, and then they can add some noisiness to that data to indicate that actually it isn't going to be perfect the way they measure what their neighbors are doing, and it isn't going to be perfect the way they implement what their neighbors are doing. So this delta Q term on the right-hand side of the equation says that there's actually some noisiness in this process. And the size of that noisiness depends on this term in red, which is called eta, and that's also a function of their local average velocity that they measure. So the basic model that we came up with is just this simple model where locusts move, they look around each other, they take an average of their neighbors' velocities, and they use that as their velocity in their next update step, plus some noise. And that noise can change depending on the size of the velocity that they measure. So this is what the experimental results look like on the top line for different numbers of locusts. And then on the bottom line, you can see the output of the model. So with 5 locusts, you can see there isn't much coordination or alignment, and that's the same in both the model and the data. Oh, I'm somehow going backwards through the talk. Any ideas? Someone else controlling the talk? Right. Okay. So when we have 60 locusts in the arena, you can see that the um, locusts stay aligned in the experiment, and they also stay aligned in the model. And then you can also see that we have an intermediary number of locusts in this model. So the data shows switching between different values of alignment, clockwise and anti-clockwise alignment, and the model does the same sort of thing. The only real difference in the model is that actually this switching is going on a bit faster. So the locusts it's not quite replicating the period of stability of these locusts. So we thought we'd better update this model. And in order to update it, so all the details are in this paper, which is all about trying to understand the way that locusts use noise constructively. In order to update this paper, and then this is another slightly mathy slide, we wanted to change this noise term here to make the locust actually change the randomness of their motion as a function of the velocity that they're measuring. So previously it was just a constant, there was no difference there, but actually then we make this into a function of the locust's average velocity. And all this function says, you don't need to worry too much about it, but it basically says when the locusts measure a low absolute velocity, so they find themselves out of line with their neighbors, they increase the randomness of their motion. And when they measure a when they measure a high absolute value of the velocity, so all going clockwise, all going anti-clockwise, they decrease the noisiness of their motion, and that helps them to stay aligned for longer. So we plugged that back into the model, and then here's a comparison. Here's the original data time series. Here's the original model time series, so lots of fast switching. And actually, when we plug this into the new model, you can see the switching time actually is much slower now, and it replicates the data much better. So these locusts are actually using noise in a constructive way to change the way that they stay aligned with each other. When they find themselves out of line with their neighbors, then they tend to increase the randomness of their motion. And so we thought, what's the reason? Why are they increasing the randomness of their motion when they find themselves out of line with their neighbors? And one reason that we thought might be prevalent is cannibalism. So one of the best ways for locusts to get protein and salt into their diet is actually to eat other locusts. And actually, during experiments, you find that if you anesthetize the back legs of locusts, then they will just sit there quite happily while other locusts start munching on their legs behind them. So cannibalism is actually a factor which is really driving these swarms onwards. So lots of interesting experiments about cannibalism, and one in particular that was done actually on Mormon cricket. So here's a lovely gruesome picture of locusts eating each other. It's a real thing. One particular experiment that was done actually with Mormon crickets in the desert in Utah was to take these crickets, stick them down by their belly onto a piece of cardboard, and put them in 4 different orientations with respect to an oncoming swarm. So this is the swarm coming on here. And when you do that, you watch the locusts come over these crickets come over these 4 crickets that are stuck down and can't move anymore. They have 4 different orientations with respect to the oncoming swarm. So this locust has its side facing, so there's this one has its back legs facing, this one has its front facing. And when the swarm passes over them, what you see is that the ones get eaten the most are actually the ones with their sides facing the oncoming swarm. And the idea is that if you've got your back legs facing the oncoming swarm, then the locusts can kick out and can actually stop the locusts trying to eat them. If you've got your head facing the oncoming swarm, then the locusts know that you can see them, so they don't try and eat you. But with your sides are vulnerable to the oncoming swarm, and so you get eaten more if you have your sides. So the idea is that these locusts somehow, when they find themselves out of line with respect to their neighbors in an unaligned state, they sort of panic, not actually panic, but they have a mechanism which allows them to increase the randomness of their motion, and that helps them find themselves back in an aligned state with respect to their neighbors. So using randomness when you find yourself out of line with your neighbors can help you get back into an aligned state, and it can keep locusts aligned for longer when they reduce the noisiness of their motion when they find themselves back in an aligned state. So that's basically all the experiments I wanted to tell you about today. So I'll just summarize by saying that locust behavior, we can model this using mathematics. There are lots of different types of models. The stochastic differential equation model, which gives you the switching, these self-propelled particle models, which are perhaps more appropriate for full locust models in the field. We know that locusts increase their individual randomness when they find themselves unaligned with respect to their neighbours, and that can help the swarm stay together. And we also are aware that cannibalism is an important driving factor for these swarms. It helps to keep them moving forward, but it also means that it's dangerous to fall out of line with your neighbours, which can help these locusts continue to stay aligned and stay stable for longer. So I'll just finish by acknowledging all the people who've put in work into this project. So in particular, Jerome Bull, who was on the call earlier, he is actually now Adelaide rather than Sydney, but he has been really instrumental in bringing this work together. And yeah, all the other people who've worked both on the experimental side and the modelling side. Thank you guys for listening.